Welcome to This Explainer. Today, we're jumping straight into literally one of the most mind-blowing events in modern math. We're going to break down exactly how an artificial intelligence, specifically the model GPT-5.4 Pro, managed to completely crack a legendary mathematical cold case. I'm talking about a problem that had thoroughly baffled the top human minds for decades. It's this incredible story of brute computational force, chaotic digital reasoning, and then ultimately this really beautiful collaboration between human and machine. Okay, let's dive right into this. 80. Just 80 minutes. That represents the absolutely unbelievable amount of time it took this AI to solve what's known in the math community as Erdős Problem number 1196. Just over an hour. To really put that into perspective for a second, human mathematicians had been attacking this exact same problem using literally every single tool at their disposal for over half a century. They were writing paper after paper, grinding out these tiny, incremental bits of progress, and then, bam! In 80 minutes, a machine just spits out the key to the whole thing. To truly appreciate the massive scale and the really high stakes of this 80-minute sprint, we've got to look at the history here. The legendary mathematician Paul Erdős first introduced the core concept way back in 1935. Decades went by, and then in 1968, the specific conjecture, Erdős Problem 1196, was formally posed by Erdős alongside Sarkozy and Samaridy. For generations, brilliant people chipped away at it. Then, suddenly, in April of 2026, GPT-5.4 Pro just solves it. It's a staggering acceleration of discovery, right? But what exactly was it that the AI solved? Section 1. What are primitive sets? So to understand the magnitude of this breakthrough, we first need to quickly ground ourselves in the math. The whole problem revolves around something called primitive sets. Now, don't worry if you don't have a PhD in number theory. We're going to use a really simple analogy so we don't get bogged down in the jargon. A primitive set is basically just a group of integers where no single number perfectly divides into another number within that exact same group. Think of it kind of like a generational family tree, but with one very strict rule. No direct ancestors are allowed in the same room together. So if you are in the room, your parents, your grandparents, your kids, and your grandkids are absolutely forbidden from entering. And this brilliantly illustrates the concept in action. Let's apply that family tree analogy to a couple of examples. Think about the numbers 2 and 4. Because 2 perfectly divides into 4. It's like a parent and a child hanging out in the same room. That breaks our rule. So it is definitely not a primitive set. But what if we have 2, 3, and 5? None of these numbers divide perfectly into each other. They are more like siblings or cousins. There are no direct ancestors. Therefore, that is a primitive set. Erdős Problem 1196 was all about calculating the maximum possible size or weight of these sets as they stretch out infinitely. Section 2. The AI's clever math trick. For decades, humans tried to calculate this infinite weight, but they just kept hitting a wall. They kept losing mathematical precision along the way. So how on earth did the AI bypass decades of human gridlock? Well, it turns out the machine used a completely different toolkit. When humans tackled this, they generally translated the problem into continuous, Archimedean math. Heavy calculus, real numbers, mostly focusing on the largest prime factor of a number. But the AI? It stayed entirely in the discrete, arithmetic world. It used these complex probability models called Markov chains, and rather than just looking at the largest prime factor, it tracked all prime factors. It utilized what mathematicians call the full adelic structure. The AI employed what's known as a downward divisibility process. Imagine a massive network of pipes. You pour water, which represents our large starting number, in at the very top. As that water flows downward, the pipes split, dividing the number by its prime factors step by step. The AI used this highly specific mathematical rule, called the von Mangoldt weight, to determine the exact probability of which pipe the water would actually flow down. By tracking this flow, the AI completely bypassed the messy calculus humans were trying to use, and it found a purely discrete path straight to the solution. Section 3. Auditing the AI's mind. Now, spitting out the proof in 80 minutes is really only half the story. Once the AI gave us the answer, human computer scientists and mathematicians had to essentially go in and figure out how it got there. This led to this super fascinating interrogation phase, where researchers audited the 55-page black box of the AI's reasoning trace. They wanted to understand its thought process. And what they found was surprising. The 55-page trace wasn't just pure magic. The machine didn't just instantly possess omniscient knowledge of the right answer. Instead, its mind generated this deeply messy thought process, full of dead ends, wrong turns, and totally chaotic iterations. It was constantly just repairing local errors as it kind of stumbled through the mathematical landscape. Now, what's really interesting about this is an observation made by the computer scientists who audited the AI. They noted, and I quote, "The winning branch was retained not because it had fewer defects, but because its defects were more repairable." That's huge. The AI didn't succeed by having some flawless, elegant master plan from the start. No, it succeeded through gritty, opportunistic local repair. It essentially threw a bunch of ideas at the wall and pursued the ones where the mistakes were just the easiest to fix. Demystifying the machine's mind really reveals a totally different kind of problem solving. There was absolutely no single, clean, top-down plan. Actually, scratch that. It was the exact opposite. The AI just kept shedding structural debt as it went. It relied relentlessly on an opportunistic search, basically filtering out unviable ideas one by one. Whenever it ran into an uncertainty, it just turned it into a localized mathematical check. It won through this process of relentless, brutal, iterative filtering. Section 4. Humans perfect the proof. Let's move on and see how this builds up to the final resolution. The AI found the path, sure, but the path it left behind was a complete tangle of chaotic probability models and a messy 55-page trace. This is where human ingenuity had to step back in. Top human mathematicians, including the renowned Terence Tao, teamed up to polish the AI's raw, chaotic output into something truly beautiful. Terence Tao analyzed those complex Markov chains and realized they were actually hiding a much, much simpler structure. He stripped away all the messy probabilities and distilled the AI's core insight into an elegant framework using simple flow networks. This culminated in his brilliantly clean, discrete divergence theorem. Going back to that water pipe analogy from earlier, Tao essentially proved that in this specific mathematical flow network, if you look at any finite set of numbers, the sum of the divergences perfectly equals the outflow minus the inflow. By removing all those complex probabilities the AI used and replacing them with this clean, discrete flow network, the proof suddenly became astonishingly elegant. It went from a chaotic mess to something incredibly easy to verify. The human refinement made the solution so clean that Terence Tao himself pointed out, this may end up being one of these math problems where the a posteriori difficulty of the problem is actually significantly lower than the a priori difficulty. To put that in plain English, this 60-year-old seemingly impossible problem actually looks fundamentally simple in hindsight. We just needed to see the problem through a completely different, non-human lens to finally spot the hidden doorway. Section 5. The future of math. So the crucial point is, what does all this mean for us? We've got this incredible event, an AI brute-forcing a novel path, and humans extracting profound elegance from its messy footprints. It forces us to look forward. We just witnessed an AI solve a 60-year cold case in 80 minutes. But more importantly, it uncovered a valid discrete method that generations of brilliant humans had entirely missed. Yet, the AI didn't finish the job alone, did it? Human mathematicians had to step in to extract the beautiful generalized theories from the AI's chaotic mess. What we're seeing here is absolutely not the end of the human mathematician. It's actually the dawn of a new era of mathematical synergy, which leaves us deeply pondering the philosophical implications of this new technological partnership. As AI models become increasingly capable of seeing paths through the mathematical universe that are literally invisible to the human mind, we have to ask ourselves, will AI eventually replace mathematicians entirely? Or will it simply become the single most powerful lens we've ever built to help us see the universe more clearly? Thank you for joining me for this explainer. Keep wondering and keep learning.